Hello, I'm Andrew Vaziri, and this video will explain the undergraduate research of Sivrat Jain and myself. This undergraduate research is the derivation, MATLAB modeling, and Texas Instruments C2000 implementation of recursive linear least squares parameter identification technique specialized for use with DC motors. So that's a lot of words, but I think to understand this, it's first easiest to break it down into what are all the hardware components. So of course we have a power supply, and we have our DC motor that we will be identifying. All of the brains of the project are in the TI C2000 control card here, and on this particular breakout board we have a lot of different kinds of peripherals. I think this is referred to as the exploration board, but we will be mostly just using the PWM capabilities and the quadrature encoder reading abilities. As you can see, we have a quadrature encoder here on this DC motor. To interface between these, we of course need a circuit, which consists of a full bridge to provide power to the motor, which takes the input of a PWM signal from the control card. And it has a few additional components here, such as a logic level converter. The quadrature encoder runs on 5 volts. The C2000 is 3.3 volts. And likewise, the PWM needs to be stepped up from 3.3 to 5. There are a number of different capacitors on this board. Some of them are for power conditioning. Other ones are charge pump capacitors. So now that we understand the components of the system, let's talk about all of those different adjectives in the title. So first of all, parameter identification. Those parameters are the coefficients of the transfer function between voltage and position, in our case of a motor. The least squares parameter identification. This means that we will be using the methodology which is to minimize the error between the observed voltage and position measurements and what would be calculated based on our identified parameters. So, in short, that just gets you the best parameters, the best fit for the actual data. In particular, we'll be using a second order transfer function. DC motors are third order in general. However, much of that behavior is due to the voltage to current behavior. However, the voltage to current behavior is what makes that third order, where mechanically a DC motor is second order. And since the electrical properties are so fast to respond in comparison to the mechanical properties, it is a reasonable assumption to use a second order model based on the mechanical quantities only. So that explains the least squares and so what makes it recursive? So we obviously have a C2000 chip here, but there's no recursive functions. There's no functions that call themselves in the idea of computer science recursion. The reason it's called recursive is because it employs a recursive proof when deriving this parameter identification technique, which allows, instead of keeping track of all of the data from the thousands or tens of thousands of samples in the past, it summarizes all of that data into one matrix of finite size, which does not grow as this system continues to run. And this reduces the amount of computation because you're only working with this one matrix, which is a 3x3 matrix in our case, rather than a matrix that is thousands and thousands of entries long. And it minimizes the amount of space you need to store this because most embedded systems have some limited amount of space, and to record a sufficient number of data points may not be possible without using this recursive method. Finally, it says specialized for use with DC motors. So what that means is we have taken the generalized theory of this parameter identification technique, which can use any inputs and outputs and describe a transfer function between them. And we have applied some of our knowledge of how the DC motor works in order to limit the amount of computation we do. So the result of this is that instead of using 4x4 matrices and 4x1 vectors, we can use 3x3s and 3x1s, which allows it to, again, compute faster and take up less space. Okay, so that explains what the final product was, but there are two portions of this project which are very significant: the derivation and MATLAB modeling. So I won't go into the derivation in this video, but if you're curious about how does this recursive proof work, how do you condense this any amount of information into one matrix, it's all available in our report. But the MATLAB modeling was absolutely vital to understanding how to create this device. For example, we went through about 6 to 10 iterations of improving the MATLAB model before we ever tried to program this on the physical device. And this is very important because each time we made an improvement, we got rid of another kind of variable in the mix. And had we just tried to jump straight into physically implementing this device, we would have had a very messy result, which would be very hard to come to any conclusions about. And it might have been the case that this project would have just stopped there as an interesting thought, but too much of a gap between the theory and the actual implementation. We used the MATLAB to describe some effects like quantization. There are two sources of quantization. The quadrature encoder has 1,000 ticks in one revolution. And while that may seem like a fair amount of resolution, when you're talking about sampling this at high frequencies, it may not move through more than one quanta, and the noise of having these quantizations becomes significant relative to how much the motor is actually moving in those very small amounts of time. There's also the quantization of the PWM signal from the control card. That has 1024 values spreading over a range of -20 to +20 volts. And if you don't account for the fact that these signals are quantized, it can cause your mathematics to be inaccurate or slow to converge, because you might assume that the voltage that the motor is seeing is an exact voltage that you've specified, when really it's receiving something that has a resolution of some tens of millivolts. So let's talk about what an actual test looks like. Now this method could be applied when the system is under control, but to allow us to compare different scenarios, we've supplied a standard input signal that will be the same between different tests. So this input signal is based on an exponential chirp. It chirps up in frequency from 0.1 to 4 hertz and then back down from 4 to 0.1. And we can specify the amount of time that this test should run, as well as how many of those cycles of up and down it should do. So let's set it to do a 16-second test, and we'll have it sweep up and down twice. So once we compile this and get it ready for debug, you'll see the test in action. And 16 seconds is actually fairly generous. It converges in more like 3 or 4 seconds, but to give you an idea of what it looks like, we'll run it for a little bit longer. So you can see that it moves a large amount when it's in low frequencies, and then when it gets up towards 4 hertz, it starts to spin back and forth rapidly. And it goes through that. It already did it once, here's twice, and then the test will stop. So now that the test has stopped, we can pause it and look at our watched variables, and we'll see that it's reporting two quantities, one called alpha and one called beta. And as we introduced earlier, we're going to be using a second order model for our DC motor. So beta is in the numerator. It's a 0th order term, and so you could interpret that just as a scaling factor between voltage and position. Alpha is in the denominator, and the denominator in total is S plus alpha. Or the denominator in total rather is quantity S plus alpha times S. And alpha relates to the inertia of the system, as well as a few other factors. So between beta and alpha, we have our result. So beta and alpha have been reported as 24 for alpha and beta of 230. And we can feed this back into a MATLAB simulation and compare what the simulation positions are versus what our actually recorded positions are from the quadrature encoder. And in that way, we can see how well we fit our behavior between the identified system and what actually happened, how it actually moved. And from our results, we've seen that the alpha term is very accurate, while the beta term is usually over-reported by about 25%. And so it's very consistently over-reported by 25%, but unfortunately, we weren't able to prove exactly why this is, and so we couldn't recommend that we use a scaling factor to correct for that, because without knowledge of how this phenomena arose, that scaling factor might be inappropriate for some systems or for some inputs. In any case, though, it's not so much of a challenge, because it's very common to analyze a control scheme in terms of gain sensitivity. So since beta is a gain term, since it's a scaling term between voltage and position, we can see if any control law that we might impose would remain stable even under a variation in gain of 25%. And in this way, we can still use these results effectively for many control. We can still use these results effectively for many. We can still use these results effectively for many control schemes, and it only really becomes an issue when you are trying to do very, very high performance or very quick response control.